In this lesson we learn the second thermodynamic principle that teaches something more about heat and work, already seen in the previous lesson. In particular, which condition needs to be satisfied when converting heat into work. This principle has three different formulations and we demonstrate the equivalence of them. Moreover, we will introduce two new concepts, the efficiency of a cycle and the definition of entropy. Since the argument is very long, we split it in two videos. In the next video we introduce the TS diagram and we make some more applications to understand the concept of reversible and irreversible transformation. In the past lesson, we have seen the equivalence of the heat and the technical or thermodynamic work in a cycle, remembering that the heat and thermodynamic work are equal and the heat and technical work are opposite. We remember that the heat of a cycle is the sum of the heat exchanged in each transformation, where the single heat is positive if given to the system and negative if given to the recipient. Let's introduce now the concept of efficiency of a cycle. For definition, the efficiency is the ratio between the thermodynamic work and the sum of Qi star, where the thermodynamic work must be positive and Qi star is positive. Qi is the heat exchanged in the single transformation. Or we can define the efficiency as the ratio between negative technical work and the sum of Qi star for technical work negative. This definition is valid only for generation machines, where the work is given to the recipient. That is the reason for the signs. The thermodynamic work is the sum of the work exchanged in every transformation, both positive and negative. If this work is negative, we cannot define an efficiency, but we can define other quantities that will be introduced later on. Moreover, it is not possible to define the efficiency of a transformation. The efficiency is only valid for a cycle. We start now with an example of efficiency. We consider a cycle in the diagram PV for a perfect gas. The mass is 1 kilogram and the transformation is so made. IB is isochoric, transformation 1, BC is isobaric, transformation 2, CD is isochoric, transformation 3, and DA is isobaric, transformation 4. We represent this cycle with a rectangle in the diagram PV. And we look for the heat and the work of every transformation. In the first, we calculate the work. The thermodynamic work is 0 because isochoric. The heat is the difference of the internal energy and assumes the expression in red. The second transformation is isobaric. The work has this expression in blue, and the heat is the difference between the internal energies of the starting and final states plus the work, also assumes the expression in red. For the transformation 3, since isochoric, the work is 0, and the Q has the expression Cv into the difference of the temperatures. For the transformation 4, the work has a similar expression as seen in the transformation 2, R into the differential temperature, and the Q has this expression also similar to the one seen for the transformation 2, Cp into differential temperature. We resume all the results in a table. And then we need to demonstrate that the heat of the transformations AB and BC is positive. To do that, we consider the transformations AB, that is isochoric. Therefore, the ratio between TB and TA equals the ratio of the pressures, and because this is greater than 1, TB is greater than TA. In the same way, we consider the transformation BC, that is isobaric. The ratio between TC and TB equals the ratio of the volumes, that is greater than 1. Also, TC is greater than TB. In the same way, we demonstrate that the heat exchanged during the transformations CD and dA is negative. So we can build the equation for the efficiency that finds the work at the numerator, that is the sum of the works of the transformations BC and dA, because the remaining ones are 0, and the sum of the positive heat, also the heat exchanged along the transformations AB and BC. So we find this expression. The second principle of the thermodynamics says that the efficiency is always less than 1. It is not possible to convert in work all the heat given to a system. Part of the heat must be taken out. This is not contradicting the first principle that says that the sum of the heat given to the system and taken out from the system is equal to the work. In this expression, we are considering only the ratio between the work and the given heat. In other words, we can write efficiency as the sum of the heat given and taken out, one positive and one negative, and the heat given to the system. This ratio must be always less than 1. We consider now a special cycle called Carnot cycle, made of 2 isothermal and 2 adiabatic transformations, all reversible. For simplicity, we assume the mass 1 kg and perfect gas. The transformations are number 1, isothermal AB, number 2, adiabatic BC, number 3, isothermal CD, number 4, adiabatic DA. We calculate now the work and the heat of every transformation. The work of the isothermal is given by one of the formulas we have seen in the previous lesson, and it is equal to the heat. And because PA is less than PB, we can see this also in the chart, then the heat is negative. For the transformation 2, the work is given by another formula already seen, used for the adiabatic, and the Q is 0. The transformation 3 is also isothermal, so we have a similar expression for the work as in number 1. And in this case, since PC is greater than PD, the heat is positive. The transformation 4 has also similar expression as number 2, since adiabatic, and the Q is 0. What is the efficiency of this cycle? The efficiency is, per definition, always the ratio between the work and the sum of positive heat, where the work is the sum of the works of every transformation, but since the work at BC is opposite to the work at DA, they remain only the work along the transformations AB and CD, also the works along the isothermal transformations. The sum of the positive heat is given only by the heat along the isothermal transformation CD and has the same expression as for the work. Therefore, we can write the efficiency in this form, while we demonstrate that this term is unity, so it remains only this simple expression 1 minus TA over Tc. And this, for definition, is the efficiency of the Carnot cycle. That is practically 1 minus the ratio between the minimum and the maximum absolute temperature of the cycle. We can demonstrate now that the expression above cancels out because the ratio between Pb and Pa equals Pc and Pd. That is the same as the ratio between Pb and Pc equals the ratio between Pa and Pd. Since Pb over Pa equals the ratio of the volumes because of isothermal, and this is also valid for the transformation CD, we can write Pb over Pa into Pd over Pc as Va over Vb into Vc over Vd. But if we consider the cross ratio in green, this is an adiabatic transformation, which is equal to the ratio of the pressures to the power 1 over k, as well as if we consider the cross ratio in blue, it is still another adiabatic, which is equal to the ratio of the pressures to the power 1 over k. And if we combine Pb over Pc together among the link and right side of the equation, and the same we do for Pd and Pa, we find the equivalence Pb over Pc to the power k minus 1 over k equals Pa over Pd to the same power, and that demonstrates above. We can demonstrate that for any cycle, the efficiency is less or equal than the efficiency of the Carnot cycle, displayed already in the previous slide. This is one formulation of the second thermodynamic principle. Another formulation is the Clausius statement. The circular integral of dq over T surroundings is less or equal to 0 if the transformation is reversible, is equal to 0 if the transformation is irreversible, is less than 0. This is a statement, we don't need to demonstrate it, but we consider that if the transformation is reversible, then the temperature of the surrounding is equal to the temperature of the system, and we can call with the same symbol, capital T, and the circular integral of dq over T is equal to 0. That means the argument of the integral is an exact differential form. We call this function capital S entropy, and this is a thermodynamic variable metered in Joule over Kelvin. This is extensive depending upon the fluid quantity, also the mass or the number of moles. And the specific entropy S is metered in Joule over Kelvin into kilogram. We define the entropy also as the integral from state A to state B of dq reversible over T. This is a definition, okay? Because it's a state function, does not depend upon the specific transformation. But we can calculate in different ways. Then we come back to the Clausius statement that says the circular integral of dq over temperature of the surroundings, because it's a cyclic transformation, we can split into the integral from the transformation A to B and from transformation B to A. And we consider for the first an irreversible transformation and for the second a reversible transformation. And we replace for the reversible transformation the definition of entropy, but because we changed the boundaries, we need to apply this delta with the opposite sign, okay? And this is negative because of the assumption above. So we can write this expression in this form. The differential entropy between the state A and B is greater than the integral from the state A and B of dq over T surrounding when the transformation is irreversible. If we have an adiabatic irreversible transformation, the heat exchanged is zero and delta S is positive. If we consider as adiabatic the whole made by system plus recipient, and remembering that the transformation is irreversible and the heat is positive when given to the system, we can consider this simple example. The heat is leaving the recipient at temperature T1 and entering the system at temperature T2. And because it is irreversible, the two temperatures must be different. And so we can write this expression and we group the heat and we find into the brackets 1 over T2 minus 1 over T1. This must be positive because of the statement number 2, but this is true only if T1 is greater than T2. So we find the third statement of the second thermodynamic principle. The heat flows spontaneously from hotter to colder bodies. What does it mean spontaneously? Without addition of work and irreversibly. From the formulation 3 derives the formulation 1. In fact, if T1 is greater than T2, then the efficiency, which is always less the Carnot efficiency, is also less than 1, because the ratio T2 over T1 is less than 1. In general, the delta S of the whole system plus surroundings or recipient is greater or equal to the Clausius integral, as we have seen before. But if the transformation is adiabatic and reversible, here we have the equal sign and the total delta S is 0. The delta S of the surrounding and the delta S of the system are opposite and are equal to the negative integral from A to B of dq reversible over temperature of the surrounding. For a cycle, delta S of the system is the cyclic Clausius integral, which is 0 because the entropy is a state function. The delta S total is also equal of the delta S of the surrounding, and it is equal to negative cyclic Clausius integral. And this must be equal or greater than 0 for the formulation number 2. Finally, we found also the definition of this formulation that says the entropy of the system plus its recipient in a cycle is always greater or equal to 0. It is equal to 0 if the transformations are all reversible. We can demonstrate, moreover, that from the formulation 1 derives the formulation 2, and we prove it by contradiction. The combination of the two machines, displayed here in the picture, gives Q2 equals 0, eta equals 1, because all the Q1 is converted into work. If the formulation 1 were not true, then it will exist a machine M2 capable to transfer the heat Q2 from the temperature T2, that is less than T1, to the temperature T1 with no work. And this contradicts the formulation number 3. Let's calculate now the delta S of the machine number 2 plus the surroundings. Actually, the machine number 2 is making a cycle, so its delta S is 0. And the delta S of the surrounding is negative Q2 over T2 plus Q2 over T1. We can group Q2 and then we have inside of the brackets 1 over T1 minus 1 over T2. And this is negative. Therefore, the formulation 2 is contradicted, because delta S of the system plus surroundings must be always positive. Resuming the three formulations, the first defines the efficiency as work divided by Q1, and the work we can express as the sum of the positive and negative heats. Here we express with a plus, but we can also express with a minus, considering the modulus of Q2. And the efficiency is always less or equal to the Carnot efficiency, having this expression. The second formulation is the Clausius inequality, where the equal sign is only valid for the reversible transformation, and then by the definition of entropy we can affirm that the difference of the entropy between the states A and B is always greater or equal to the Clausius integral. And the third formulation says that the heat always flows from hotter to colder bodies. We see now some formulas to calculate the entropy of a transformation. From the first principle, we have that the delta U equals Q minus L, whose differential form is du equals dq minus dl. We use here a different symbol for the differentials of Q and L, since they are not exact form as U. From the entropy definition, ds equals dq over T, and from the definition of work, dl equals P into dV. Also du equals T ds minus P dV, while for a perfect gas, du equals Cv into dt. Therefore, Cv dt equals T ds minus P dV. And if you divide both sides of the equation by the temperature, we have Cv dt over T equals ds minus P over T into dV. And if we replace P over T with the ideal gas equation, we find this expression. Therefore, ds equals Cv into dt over T plus R into dV over V. And by integration, we can write the first expression for the entropy as function of temperature and volume. Delta S equals Cv times logarithm of T2 over T1 plus R into logarithm of V2 over V1. And this is Joule per Kelvin, considering a unitary mass. Otherwise, we have to multiply for the mass. And using the state equation to change the variable T into P and V into P, we get the remaining two expressions. One for delta S as function of P and volume, and one for delta S as function of T and pressure. Some special cases. For isothermal, T1 is equal to T2 and remains only the logarithm of V2 over V1 times R. For isochoric, V1 is equal to V2 and remains only the logarithm of T2 over T1 into Cv. And since T2 over T1 equals P2 over P1, we can also express the same formula by using the ratio of the pressures. For isobaric, P1 is equal to P2, delta S is Cp into logarithm of T2 over T1, and since the ratio of the temperatures equals the ratio of the volumes, we can also write in this form. For adiabatic, dq is 0, ds is 0, delta S is 0. We remember for the adiabatic reversible transformation. For the polytropic, from the formula 26 and replacing V2 over V1 with P1 over P2 to the power 1 over m, we can write delta S equals Cv times logarithm of P2 over P1 plus Cp times logarithm of P1 over P2 to the power 1 over m, and if we drop down the power and inverting the argument of the logarithm of the pressures, we get this expression. And since we have a common factor, we can group the logarithm of P2 over P1, and we have a very simple expression here. So we find the formula number 28 for the polytropic, also considering the unitary mass, and if you replace Cv and Cp with the expression of R using the ratio of the heat values K, we can express delta S also with the formula 29. For the time we have finished this part of the presentation. It will continue in the next video to complete the second principle of the thermodynamics with some examples.